All right. I thought I would start on a lighter mode here. Um, so there are a couple of stories here. One is with the title itself. Anyone here heard the dialogue "On my signal, unleash hell"? Which movie? Perfect. So, so we thought we'd start with that as the title. And the reason for that is, how many of you here have heard of war rooms or incident rooms? There you go. How many of you have been involved in war rooms? Yeah? So at the end of this, I'm hoping that you get to learn a little bit more about potentially an approach that would reduce the requirement to have war rooms, right? This GIF here is from a Powerball, Super Bowl ad in the US. It's for a pizza company. This guy here is a CEO of a bread company, and he is being beaten by this pizza company using a slogan, best thing since sliced bread. And that's created this chaotic situation. I don't know how, a lot of times this happens to me, Cam, Monday mornings or Friday evenings before release. That's how, wouldn't you, a lot of people would feel like that? A lot of CTOs, CEOs probably had this feeling when, generative AI became popular over the last 6 to 9 months. Yeah, best thing since Google? Don't know, right? So that's why we thought we'll start from here. I think I forgot my clicker. But what we're going to try and talk to you about here is how chaos engineering can potentially look at reducing the risk of certain types of faults that occur in production. Okay? No, not working. Should have tested that.
This is all part of the presentation. Don't worry about that. This is right. Really cementing the point.
That's fine. We can.
Good. Got it.
We can do it. So, look, I've put the names or the types of organizations here, not having a dig at any of you here. If you work for a betting organization, a retail company that has an e-commerce platform, or a banking organization, it's just to talk to you about the impact, right? So a lot of times, and we've seen numbers like this before, right? Millions of dollars being lost when platforms, stop working on Black Friday, for example, e-commerce platforms, instability or third-party dependencies causing outages for banks before paychecks are going into their bank accounts. The one which is quite interesting, which is more closer, happened recently, was for a social media aggregator, where they made some pricing changes that caused an outage related to an API, something that nobody would have probably thought about when they made that change. So outages happen, right? No matter how much you test, no matter how much, like I think there was a session about risk we had before during the day. In the end, you're not going to go live with a completely bug-free system, right? You're going to go live with a certain level of risk, and that means that there's going to be failures that are going to occur in production. The question is, how are you going to react to those incidents? Are you actually prepared to recover from those incidents? And that's what chaos engineering is about, to an extent. And we'll talk about how you approach it in terms of ideas, in terms of tools, in terms of what can be done at what levels. So just to accentuate the problem a little bit more, who here thought that with microservices architecture and the ease with which we can deploy applications on cloud platforms, this should actually reduce the amount of failures occurring? Few people? Most of the testers would say absolutely, that's never going to happen, right? But it's easy to get started nowadays. Anybody can build a microservice, have an API that interacts with that microservice. That microservice could be developed in using different technologies. So you could have essentially a complete e-commerce platform with microservices which have been built with different technologies behind it. And there's a lot of usage of open source libraries. There's third-party dependencies. You've got dependencies on SaaS platforms like Salesforce, as an example. And what this is creating is an extremely distributed system that is potentially being deployed across hybrid cloud architecture, some within your own data centers, potentially deployed across multiple cloud platforms. And what this creates is potentially a lot of invisibility of how your systems actually perform, or what your system overall looks like in production to start with. And that's actually causing a lot more outages because the visibility isn't there. Everybody, as much as we would like to say, Agile has brought everybody closer, the silos are reducing, there's still silos in organizations, right? A lot of times I've seen organizations going the other way. You've got you've got squads who are working quite independently within their own group. They're responsible for their own bit of world, but they don't talk to each other. That happens quite a lot still. And that could potentially be related to how we work as humans. I don't know. I don't want to go into psychology right now, but effectively what I'm trying to say is this was supposed to be the promised land. Microservices, modular architectures, event-based architectures, easily deployable in cloud. You can release a lot faster, but you're still having issues. You're actually having more outages in production. All right, so this is where chaos engineering comes into picture. Now, like I've already established, no matter what you do, you're still going to have outages. There's a very good example recently. I don't know if you heard about it. Azure. Hello. Yeah. Azure had a dip in voltage in one of their data centers here in Australia. Yeah, and that caused some of the data storage systems to actually fry. And that caused outages with multiple organizations within Australia. So you've done all your testing, you've mitigated most of your risks, but there is still likelihood that you're going to have some sort of failures in production. The question here is, we are not trying to avoid those failures, we are trying to understand how we are going to essentially recover from those failures. Okay? So the types of outages that can happen is service outages, dependency failures, unexpected load, increase in latency. All of that is going to impact your applications in production. I've given a very small example down below, not a very fault-tolerant architecture there. You've got a load balancer. You've got a few services there behind the load balancer. You've got a single database instance. Obviously, when that database instance fails, you're going to have some sort of an outage. How big that outage is depends on what your application is. If it is a static content website with a couple of forms that are being submitted, it's probably not a full outage, right? But if it's an API service which is all the time talking to the database, then it's a full outage, right? So chaos engineering is about understanding or thinking about the types of faults or incidents that could occur in production based on the architecture that you've got and based on how you're deploying that architecture in production, and actually running some experiments or having an approach to actually deal with those types of failures in production. Just a very brief history. How many here have heard about Chaos Monkey? Yeah, quite a few. That's good. So it's been around for quite a while. So it's not like this is a new concept. Chaos engineering as a concept has been around quite a lot. And a lot of people here might even argue, well, a lot of us do failover or disaster recovery testing. How is this different? You would also potentially argue operational acceptance testing was one of the things that was done. We'll talk about how this is different to some of those things that you've been exposed to before. So Netflix coined this idea of chaos engineering. They had services deployed on EC2 instances. They wanted to identify when we bring down these EC2 instances, what happens to the services, what is the impact to the customers, right? So they created a tool called Chaos Monkey. They realized that, well, this is actually giving us very useful information. They started thinking about other faults that they could potentially introduce. They started creating other utilities, which in, I think, 2012 became a tool set called Simianami. And they continued building on it. They started realizing that when they're doing these experiments, there can be, unknown faults that are occurring, and sometimes it becomes an uncontrolled behavior. So they started creating more controls into those tools. And one of the ex-Netflix employees decided, well, that's probably a good idea to start a new business. And he founded a company called Gremlin, which I'm pretty sure a few people here in the audience must have heard about. And since customers have started adopting it, the cloud platforms have realized, well, we probably need to provide a service that allows customers to do this. Because in the end, they are deploying the services within their cloud platforms. And if you build fault-tolerant architectures, a lot of times you'll probably recover quite well from them. But not everybody can afford to have, applications deployed across multiple regions, as an example, right? So some of their customers would need to understand how their systems, how their services are going to behave under certain fault conditions. And they started providing inbuilt services. So there's an inbuilt service in AWS called Fault Injector Simulator. How many people here have heard about that? Almost no one, right? How many have you heard about Azure Chaos Studio? Few. So the cloud providers are actually providing services now to run chaos experiments. Go on. So just touching on benefits. So I think some of the key benefits, once you look at the approach, you'll realize how these are real benefits of introducing chaos engineering within your organization. Obviously, the key aspect here is to improve resiliency and availability of your systems. Yeah. Where you've got services that have a direct impact on revenue and reputation, it's reducing your risk to that. The key aspect here is you're trying to uncover incidents in production before they become incidents, right? So that's the key reason for doing this. But while you're doing that, you're actually going to expose a lot of blind spots. So when I talk about blind spots, when a service fails, usually you need to understand that your service has failed in the first place and why it has failed. A lot of times that information is either in logs, that information is in potentially some instrumented data, that information is potentially in some matrix, so that information is available in some telemetry data. And that telemetry data needs to have sufficient information for you to actually understand what's gone wrong with your service. And a lot of times when you're running these experiments, you're going to expose those areas and expose those blind spots if you've got some. Yeah? And that's what I'm talking about in terms of improving visibility. A lot of times, there's still a lot of organizations have a reactive approach to incidents. This is about building more proactive approaches into improving resiliency and reliability of your systems. And we'll talk about an approach later on, which actually brings a lot of teams together. So there's a concept of game days, which we'll talk about later, and that actually helps to bring different teams together so that they have a similar understanding of what your architecture actually is and work together towards resolving incidents in production. So we've talked about benefits, we've talked about why, we've talked about what. Now we're going to talk about how, right? So there are a few pillars for introducing chaos engineering within any organization. The tools are obviously there to help you run these experiments, but essentially you start with understanding of how your service or system behaves in normal circumstances. So in terms of under load, what are the response times? What is the typical error rates that you're getting for your services in production or in your non-production environments if you are running realistic loads in those environments? Are there certain types of exceptions being generated? So when you're running performance tests or when you're running performance tests in your non-production environments, which are realistic, a lot of times you're exposing some of this information. So the idea is to have this steady state. If your service is already live, you will have that information from your production environments as well, right? So the key there is to know the steady state of your system. And then the next thing is, based on your architecture, starting to think about the types of experiments. Now, when I say experiments, a lot of times you would say, well, aren't experiments just tests? Yes, to an extent they are, but they're slightly different. So this is where there's a key difference between just the failover or the DR type of testing or operational acceptance testing and chaos engineering. Those exercises are very controlled. There is a plan, there is an approach, there is an expectation that when you do something will happen, and you're validating that it's a pass or a fail. Chaos engineering experiments are not a pass or a fail. What you're actually trying to think about is all the different types of incidents or faults that could actually occur in production, not just failover, not just DR. And we'll talk about, you'll see on the next slide the types of experiments that can be conducted with some of the tools which are available, is to actually then learn from those experiments and identify your blind spots, identify your process in terms of recovering from some of these faults. So that's what the hypothesis is all about, is as an example over there, the example on the slide there is a very simple one where you're introducing some sort of a resource stress on your service. And then your hypothesis would be that, potentially the response times of your service will be impacted. Potentially you could have certain alarms if the CPU stress, for example, goes beyond a certain threshold. What you're trying to validate is whether those alarms are actually being triggered. What is the actual impact from a response time perspective? Yeah? You then run the experiments. You are then analyzing and learning from them to improve the fault, the capability of your teams to recover from when some of these faults occur. And if there are any blind spots, then you're trying to fill those gaps from those blind spots perspective. Now, one of the key things there, you would see there's a concept there called blast radius. So what this talks about is the impact of your chaos experiments. So like with, we talked a lot about shift left previously today. You can always start small. You don't need to start with a fully integrated production-like environment to start running chaos experiments. You can start at your component level, at a microservice level. There are certain experiments that you can conduct at that level, learn from them. Like, for example, when your service has a failure, what information it is logging for that failure is something that you can easily do in potentially even a dev environment, right? So you can start there. Once you have learned about your individual component service, when it fails, let's say if you're deploying it in a Kubernetes cluster, when a pod fails, something as simple as that, you can then start looking at dependencies. So you can then move on to a potentially an integrated environment where you've got dependent services connected to each other, and then try to understand when these dependencies fail, how your service is impacted. Same thing with the other service, how that service is impacted when your service is not working. So that's how you slowly start increasing your blast radius. And then you move towards more your production-like environments. That's where you're running experiments where you're going back to more your region-type failures in cloud, doing the failover from one data center to another in cloud. When you say availability zone, that's just essentially another data center, right? So you can then run more large-scale experiments in that higher environment. So I've just given a brief overview of some of the experiments, and this is where you will learn that it's a lot more than just running some DR and failover tests, right? There are faults that you can introduce which are your application or service related, infrastructure related. If you're deploying in Kubernetes using containers, then there are certain faults that you can introduce which are specific to that deployment mechanism. There are cloud-specific faults that you can generate, database-specific faults, even network-specific faults like packet loss and bandwidth limitations and things like that. So essentially, if you look at some of the examples there, it's all about, well, when these conditions occur in production, when these faults occur in production, how are your services behaving, and what does your recovery process to those failures is actually going to help you get to the root cause quickly enough before it becomes a major incident, which is causing revenue or reputation loss for your organization. All right, so we've kind of talked about the why, the how. The other aspect of it, if you have not already started on this journey, is well, how do I get started, right? So, like with any other new concept that you're introducing to an organization, there will be questions asked, right? Why do we need to do this? So we've kind of talked about that why, but then you need to educate some of your key stakeholders. That would be business stakeholders, product owners, technical product owners. That would be your technical stakeholders themselves, who a lot of times will be very supportive. Most of the times when we have talked to customers, especially the technical stakeholders, they're always for starting to think about running these types of experiments. Communication. So like usually when you're introducing something new, you obviously need to identify what works best for you. So do we start with our lower environments, or do we start with some other approach, right? Where are you going to actually execute the test? The environments, there will be a cost impact. So all of these things obviously need to be talked about, thrashed out, agreed upon before you start on this journey. And then how do you do it? So what tools can we use? So we'll talk about a little bit about the tools, and we also have got a demo for you today. Can we shift left? All right, we were talking about smaller experiments. How can we bring these experiments more closer to our lower environment so that we learn about these faults early enough before they are becoming outages in production? All right, so that's a bit of an example there. The graph is talking about, the complexity of running these experiments obviously is going to be higher in your more production-like environments. But the level of assurance you're going to get is also going to keep increasing as you run these experiments. You can run certain types of experiments in your potentially lower environments, even such as dev environments. The failing dependent services, databases, you can run that in your integrated environments. Then adding, scaling specific faults or network latencies, that's something that you can do in your staging environments. If you research about this topic on the internet, there's a lot of articles which will talk about you should be doing this in production. It's not for everybody, right? If you have got services like e-commerce platforms, if you are introducing faults in production and that causes an impact in revenue, you could potentially do it at 2 o'clock in the night when the impact on revenue is probably going to be smaller. But still, it's running in production, always a risk. What happens? Well, are you going to be able to recover quickly enough is probably a question that's going to be asked. So maybe not prod, maybe pre-prod, maybe staging. That's where you would run more the traditional DR failover type of exercises. But the idea here is that you build it up. The complexity will increase, but the level of assurance is also going to increase as we do more experiments and learn more about these faults. The risks and challenges. So obviously, if you can think about it, we started with this idea that this is a very chaotic thing that you're doing, right? So, and that's what sticks a lot of times in the minds of stakeholders is, well, this is going to be very difficult to do, and you have to talk about this with your stakeholders. Is yes, there will be risks. You could identify things that you didn't expect to find when you're running these experiments. If I've had situations where, non-production environments are somehow still connected to production dependencies. How many of you have had that happen before? Yeah. Right? Your environment, the one, especially if you're using shared environments, that could have an impact in terms of recovering from some of these failures. Cascading failures is one of the big things that we have seen that happens when especially if you cannot control your blast radius. And then the cost associated with it, the operational overhead, because you need to bring people in to actually run some of these experiments. You can't just run it independently by yourselves. You'll find observability gaps, and one of the things that we talked about there with the steady state was observability is extremely critical for you to be able to run these experiments. Because if you can't, if you can't identify what has failed and where it has failed, it's not going to help you in terms of getting to the root cause and recover from those faults. And there will be skill gaps. As you are starting on this journey, it will take time for your teams to understand the concept, understand the benefit that they're getting out of it. So there will be some time before you mature with any any new framework, any new service that you are introducing to an organization. It's always a challenge. So we've talked about how this can be incorporated into your release or delivery lifecycle to an extent by running certain types of experiments early. But one of the things which is quite popular, and you would hear about this when you research this topic on the internet, you would hear about something called as game days. Okay, so this is quite a popular idea of running chaos experiments and can be quite beneficial. Now, obviously, why run game days? Now, one of the things that I've always found is quite interesting is you have, you've got when you're deploying any system, right? There's a lot of a lot of people involved. You've got your developers, you've got your testers, you've got architects, you've got product owners, you've got people who are going to support the application in production. When your system, especially if you've got microservices architecture, you've got third-party dependencies, everyone has got a different mental picture about how your system actually behaves, how those dependencies actually manifest as failures, right? The game days actually bring a lot of these stakeholders together, a lot of these team members together, and you get a common understanding of how your distributed system actually works. So that's why this is quite popular. You're actually bringing a lot of these teams who are going to make changes to your services, to your applications, who are going to support these applications in production. And you're going to generate these failures, and you're going to all together understand how these failures are manifesting, how long it's taking for you to actually understand what has failed and recover from it. So it's almost you're testing your capability of recovering from an incident in production before it becomes an incident. The same thing that I was talking about in terms of introducing chaos engineering to your organization, you have to do the same thing in terms of planning your game days. You have to educate your stakeholders. You have to obviously schedule workshops with some of the key stakeholders to define the experiments that make sense for running game days. So, for example, if you've done some of this, some of the smaller tests have already been executed in lower environments. They probably don't make sense to run again as game day. So you do need to have workshops in terms of planning this, and obviously the logistics in terms of bringing people together. Now, one of the ways to make it fun is run it like a game day, gamify it. So similar to bug hunts, similar to hackathons, run it something in that fashion. So that way, people are interested in it. They are having fun. They are essentially learning and enjoying that whole exercises rather than thinking about, oh, what am I going to do here when a failure occurs, right? The key aspect there is the experiments that you're running need to be related to potentially real-world incidents that will happen relative to the architecture that you've got. And what you also probably need to capture is the troubleshooting that some of the key team members who are going to support this application are performing, because that will help you identify the gaps. That will help you keep you informed in terms of how long it's going to take to recover from some of these failures. And that's going to open a very good conversation between various teams. Now, I was talking to someone before, and they talked about the fact that when you run game days, there have been people in the organization who have not seen each other or talked to each other for a few years, but when they're running game days, they come together and realize that they actually support the same application. So it can help improve collaboration as well. This is a very brief view of some of the features that you would look for when you're choosing tools to run your experiments. There's obviously commercial tools available. There are open source tools available. I think Gremlin is the one which is quite popular. Litmus is also something that's becoming quite popular. We are going to have a demo today. Suraj is going to run through with the AWS FIS toolset. But effectively, what this table is showing you is some of the things that you need to think about when you're choosing tools. And for every organization, it might be different. Yes?
All the demonstrations now, so what you're saying is chaos means push it. Does it mean push it to the limits?
Not necessarily. It's all about thinking about what incidents could occur related to your application. So as an example, right, the example that I was giving you before around Azure disks, disks being fried, right? So it's all about simulating, well, if the disk storage network, if the disk storage is completely unavailable to your system, how does that fault actually manifest itself? What is the actual impact? How long does it take for us to actually realize that something's gone wrong? So for certain applications, that could be, depending upon how well they have got observability, depending upon how well they have got the amount of logging information that helps you troubleshoot those issues. For some, it could be a few minutes. For some, it could be a few hours. So it's all about learning from what incidents would make sense for your particular architecture. Yeah. As an example, the other one that I was giving you before around, not a fault-tolerant architecture, just a single database, right? How does that actually manifest from an end user's perspective? Okay. Once you know that, you obviously are going to put in a more fault-tolerant architecture and rerun some of these tests. And then at that stage, you are expecting that you're going to fail over to a secondary database. But then when that secondary database failover is occurring, how long does it actually impact in-flight transactions? How long does it take to failover? All of this information is very, very useful for people who are supporting these systems in production. And a lot of times, if this is not done, they're finding out about these things when they go live, right? And these incidents actually occur in production. So it's all about trying to mitigate those risks by knowing the unknowns to an extent. Yeah. All right, I'll hand over to Suraj now to talk about the demo.
Yeah, cool. Thanks, Kedar. Hi, everyone. So for this demo, we have deployed a simple e-commerce application which is available publicly through Open Telemetry contributors. This application is deployed in a Kubernetes cluster in the EKS AWS service. The cluster has got 2 worker nodes, and the nodes are part of an auto-scaling group with a desired instance count as 2. As Kedar mentioned about the chaos, a lot of cloud platforms now offering services to run chaos tests. And for AWS, that service is called Fault Injection Simulator or FIS. We are using AWS FIS to inject fault in the application for this demo. Based on the above architecture, now we are going to conduct a very simple experiment of terminating one of the worker node inside the Kubernetes node group. As per our hypothesis, when we terminate one of the worker node, the Kubernetes containers running on the nodes will be also terminated, resulting in bringing down the demo application. Yeah. Since the node groups are part of an auto-scaling group with a desired instance count as 2, the auto-scaling group will create another instance and the Kubernetes containers will be recreated on them. We are expecting our application will recover fully on its own. Now I'm going to play a recorded demo where you will see these components and our video and hypothesis in action.
So what is your hypothesis here, Suraj?
So our hypothesis is, like I said earlier, in this architecture, there are 2 worker nodes, and we will be terminating one of the worker nodes, which means that those worker nodes are part of an auto-scaling group with minimum and desired instance count as 2, which means that auto-scaling group will create another instance which will join the EKS cluster automatically. And we are expecting the containers will be recreated on them. And our demo application is expected to recover fully on its own. Yeah. Now I'm going to play the demo video. So as you can see, this is the sample demo application It's just a plain e-commerce application backend by few microservices. In this application, you can browse products, add them to cart, so it's not playing. In this application, you can browse the products, add them to cart, select quantity and place an order. While we'll do the chaos fault injection, we are expecting we'll see some failures on this application. Now I'm going to show you the list of the worker nodes and the containers running on the nodes using the kubectl command line tool. You will see there are 2 worker nodes which are in ready status. We will be terminating one of these nodes. You can also see the list of containers running on these nodes. As you can see, for example, each service, the currency service or a checkout service are running on a separate container. Also, there is a single container running for each service. So this is definitely not a fault-tolerant deployment architecture. We are also running a small load test against our demo application using a tool called Locust. This tool provides us observability dashboard and also help us to understand the impact of our fault tolerance experiment. As you can see in this load test, there are no failures as of now because the demo application is up and healthy. But once we'll inject fault using AWS FI's tool, we are expecting we'll see failure in this load test. Now I'm going to talk briefly about the AWS FIS. AWS Fault Injection Simulator is a fully managed service for executing fault-tolerant experiments in AWS. If you are using AWS resources, it should be your tool of choice. And if you are deploying any kind of application in AWS, this is one of the best tool available. It lets users to create experiments with the real-world condition and also provides controls and safeguards to run experiment in any environment like production. For the services deployed in Kubernetes, there are a number of different experiments which are available out of the box with AWS FIS, like port termination, node termination, port CPU IO stress, network latency, black hole, etc. For this demo, we are going with the node termination experiment. As you can see, we have already started one experiment. An experiment template basically contains 2 important steps. One is to select a fault injection action type, and the other step is to select a target resource for your action. Like you can see, the experiment has started. Now we are going to check the status of the worker nodes. As you can see on the screen, one of the worker node is it's in not ready status. That means that worker node will be soon removed from the cluster. You can also see the status of the containers running are changing from running to pending or terminating. So in around minute period, these containers will be removed. You can also see on the screen now, if you go back and reload the demo application, this application is not loading because the underlying services are down. Now what we did, we paused the recording here for a couple of minutes to allow auto-scaling group to create another EC2 instance which will join the cluster. So after a period of 2 to 3 minutes, we saw another EC2 instance has joined the cluster. As you can see, its status is ready and its uptime is nearly around 2 minutes. You can also see the container has been restarted and recreated on them as per our hypothesis. Now if we go back and check our Locust load test, we might see failures there which is expected. As you can see on the screen, there are failures in our Locust load test. If we check the total request graph, you can see the red line graph which represents the failures. Those failures started when we injected the fault in the application, and this failure lasted for nearly around 4 minutes period. After that, the test recovered, which was our hypothesis. You can also see in the bottom response time graph, there is a huge spike of nearly around 130 seconds. So clearly it states that some of these requests might be waiting for the underlying services which were not available. So it kept on waiting and there is a spike. Yeah. So this was a simple demo to show you how we can implement a fault tolerant against an application. Like Kedar mentioned earlier, during the chaos engineering approach, we should always start with a small experiment and take learning from the experiment. So here one of the learning which I observed was there was a single container running for each service, for example, cart or a checkout service when that container was terminated, that service was not available. So we saw failure in the locus load test. So to make it fault tolerant, we should have at least 2 containers running for each service. Yeah. So that's all from this demo. Now I will pass it to Kedar to conclude this presentation.
All right. Thanks a lot for that, Suraj. So, look, we've, when Cam introduced us, we've been working in the performance engineering space for quite a long time, but I can see that the conversation is moving beyond just performance, and resilience and reliability is becoming extremely important. What we've given you here is some information around a concept that can help you get started towards introducing that in your organization if you're already not doing that. But the other aspect there is also the fact that if you've got an extremely distributed microservices and event-based architecture, you've got third-party dependencies, you're deploying these services, especially in cloud platforms, there are options available now with, especially with AWS and Azure, to start running these experiments within your environments, right? And from the demo perspective as well, we've put together a very simple demo. As you can see, our hypothesis was proven right, but some of the things that you would learn from this as well is, well, a locus dashboard is not sufficient from an observability perspective. You probably need a better observability platform to actually understand how your systems are failing. So that's also extremely critical. And with that, I will conclude. And now we've got a couple of minutes for questions, Cam?
Perfect, man. Yeah.
Yep.